Part 1 of the 4.5 notes, we're going to be talking about graphing rational functions. We're going to be analyzing the graphs of rational functions, but I wanted to remind you that rational functions are just one polynomial over another polynomial. Okay, so poly over poly. And so please remember that when I ask that question. Here's some examples of polynomial functions. And sometimes if you think, okay, polynomial function, well, I know that x is a polynomial function. I also know that 3 is another polynomial function. That happens to be a constant, but it's still in the polynomial family. But nevertheless, this is not a polynomial function, just like x over 2 is not a polynomial. The denominator must have a degree of 1 or higher. So the degree must be greater than or equal to 1. So that's what will make you a rational function. Okay, and also the degree has to be, remember, the degree has to be whole, or the exponents have to be whole numbers, and the coefficients have to be real. Okay, so let's go ahead and take a look. We're going to analyze this graph. You can see f of x is here defined to be x minus 2 over x squared minus 9. And analyzing the graph of a rational function, just like we've done with polynomial functions, but with in terms of the things that we're looking for, polynomial functions, though, never have vertical asymptotes and they never have horizontal asymptotes either. So that's one thing we get to look at when we're going to be talking about rational functions. We still have intercepts, holes. There's things that polynomials don't have, but still domain range, and we're going to talk about the extreme values of these functions as well. So the first thing we want to do is factor the numerator and denominator, and so let's go ahead and do that. If we factor f of x, the numerator is already factored, x minus 2, but the denominator, x squared minus 9, we're going to factor that using the difference of squares pattern that we know and love, x plus 3 times x minus 3. Okay. Now, this function f is in lowest terms, because once you factor, if there is the ability to cancel any of the factors, then you're going to do that, and then you'll have lowest terms. Okay, so that's what we consider lowest terms. We're going to be now locating the intercepts. So if we want to know what the x-intercept is, that's when the numerator is equal to 0. Okay, numerator equals 0. Now, why just the numerator? Well, because when the numerator is equal to 0, the y is equal to 0. So the function has a value. Should put f of x. So when the numerator is equal to 0, that's the only way you can make the function's value equal to 0. And remember, the value of the function equaling 0 means that it's right on the x-axis. Okay, so if ever the value of the function is equal to 0, that's when we have our zeros, and we talked about that. So zeros of rational functions are the same concept as zeros for polynomials as well. You know, it's what makes the function's values equal to 0. Okay. Well, we can see here clearly that the numerator equaling 0 only happens when x is equal to 2. So there's our only x-intercept. Okay. So we've got that. Now the y-intercept, on the other hand, is when you just let x equal 0. Okay, so let's do that. So we know that the y-intercept, let me do this. Let me erase this here so I have a little bit more room, because then we're going to be doing more things than just that. I wrote that pretty big, that x-intercept. Nevertheless, I'll erase it if I need to. So the y-intercept, that's when x is equal to 0. Okay, well, when x is equal to 0, we have the value of f of 0. So f of 0 is 0 minus 2 over 0 squared minus 9. And so we just get 2 over 9. Okay, well, that's great. And then we're going to switch gears here. We're going to go up here to the right-hand side. Number 3, I guess we could call this. We're going to try to find the ha and the va. Ha and va. Okay. Well, the ha and the va, to find the horizontal asymptote, we just look at the function f of x is proper. Okay, we talked about that, I think, in the last video. but f of x is proper, therefore y equaling 0. This is the bubble theorem, don't forget. Bubble theorem says the bigger bubble is on the bottom. This function doesn't go anywhere, and so therefore y equals 0 is the ha. Okay. And what about the va? Well, we talked about that in class. If we can't cancel the factors, all these real numbers really want to be the vertical asymptote, and the only ones that make the denominator equal to 0 are the ones that we can even consider. Okay, so these guys are in the playoffs, x equals -3 and x equals +3, and neither of those factors, by the way, got canceled, so those are in fact the vertical asymptotes. Okay. Now, the other part here is we want to figure out what the shape of the graph would be, the behavior near the horizontal and vertical asymptotes, and then domain and range. Let's talk about the domain and range. Okay. Let's see. Domain would be all real numbers x such that x cannot equal plus or minus 3. Okay, because that's what initially makes the denominator equal to 0. And the range, well, let's determine the range from after we graph this function. Okay. Please write this stuff down. I'm going to have to erase some of this so that we can so I have some room to do the rest of this. Well, we already know it's lowest terms. Let's see here. Let's do this. I'm going to erase this. We already know x equaling, so you have the x and the y-intercepts written down, right? Okay. Vertical asymptotes, x equals +3 and x equals -3. So we have one of them there. Oops, I don't need a dot, we need vertical asymptote there. Okay, so we have vertical asymptote here. What we're going to do here is we're just going to write down and make a picture of everything we know so far. Okay, so we have our vertical asymptotes. We have our x-intercept. Remember our x-intercept? That was equal to 2. Okay, so we're going to draw the graph right there like that. Put a dot right there, and then we're going to have another dot right here at 2/9. Remember 2/9 was our y-intercept? So those are our only intercepts. Okay, so then we notice that we have 4 over here. We have 3, 2, and 1. -1, -2, -3, and -4. Okay, so the graph has to go through these 2 points on the y and the x-axis. So the graph has to do this, behavior near asymptotes. That was bad. Let me zoom in a little bit on my end so I can do this better. Behavior near a vertical asymptote, either the graph, the y values are either going to go way up there to positive infinity or way down here to negative infinity. So the easiest part of this graph is to look at the asymptotes, vertical asymptotes inside, because we already have dots, we have points on the graph. So if we don't have any points on the graph, we're not sure which way it's going to go. But keep in mind, if you have a vertical asymptote, then the graph of the function is going to either go way up to positive infinity or way down to negative infinity on one side or on both sides. So we'll talk about what's happening on the other side here in a minute. Okay, so now we know that y equals, remember y equals 0 is a horizontal asymptote. So if we put a dotted line right across the x-axis, we can remind ourselves that that is in fact a horizontal asymptote. That's our only horizontal asymptote. Okay, notice here, guys, that the graph of the function f of x actually does cross the horizontal asymptote, and so that's okay. It's okay to cross a horizontal asymptote. All right. Well, what else do we need to do here? Well, what we need to do is we need to figure out whether the function goes like this or it goes like that. Okay, now notice that I did just these last two that I did. I drew the graph like that because it's going to either go way up to positive infinity or it's going to go way down to negative infinity. And if it's down here, remember that y equaling 0 is a horizontal asymptote, so it has to go out that way or out that way. Okay? And so we're not sure yet. We have to just determine that from plotting a couple points. So that's what we're going to do now. We're just going to figure out what side. And by the way, same thing with over here. It's going to be one of these. It's either above the x-axis here or below the x-axis there. So it's got to look like those because the domain is all real numbers, remember? All real numbers except for 3 and -3. So we better account for all those real numbers if we're going to be drawing the graph. So the easiest way to do this is just to make an x-y chart with two values in there. We're going to put the number just to the right of the positive vertical asymptote. We're going to put a 4 in. Okay? And what is y when x is 4? Well, we look back at the original function. We have 4 minus 2 in the numerator. And in the denominator we have 16, 4 squared, minus 9. So clearly that's positive. That's all we need. But let's go ahead and figure out what it is. 2 over 7. 16 minus 9 is 7, so 2 over 7. So when x is equal to 4, y is equal to 2 over 7. Okay, you don't have to get too particular about that, but I will draw the graph in blue. Okay, so there's that part of the graph. And then we're going to choose another strategic value for input. And the next strategic value would be x equals -4. And if we put -4 in there, we're going to get -4 minus 2 over 7. So that's -6 over 7. So -4 squared, 16 minus 9 in our denominator. So we get -6/7. So that's clearly less than 0. And so if it's less than 0, then we're going to have something down here. And let me, well, something down there. We'll just draw the graph again in blue, right through that point. And it goes all the way down like that. And that, guys, is the graph of this function. Did we answer all the questions? Domain, range? Oh, we didn't answer the range part. So the range, if you just look at this middle section in here, this middle section, this middle part of the graph, I should say, accounts for every single y value. And if it accounts for every single y value, guess what? That means that the range is all real numbers. I know it doesn't look like the range is going to be all real numbers, but all you have to do is remember that the range tells us, or when we're discussing the range or coming up with the range, answering a question, what is the range? We're answering the question, what y values are used to graph the function? And you can clearly see, hopefully, that every single y value is being used to graph this function. And guys, that's how to analyze a rational function. I don't think there's anything left. Oh, holes. So we didn't talk about any holes because this graph has no holes, but our next example will have some holes. And as far as extrema goes, we can hopefully clearly see that we have no extreme values. It has to be a value in the range that is the lowest or the highest, and so we don't have any of those. Okay, we don't have any high or low points. Okay, so that's it. Next video.